Hello and welcome to section 5.1. In this section we are going to be talking about the natural log function differentiation and a little bit of integration with it. And so in this section, if we are asked to, the natural log is basically defined by the integral from 1 to x of 1 over t dt. So basically what we're saying is if we tried to integrate a function like 1 over x dx, this is really the integral of x to the negative 1 dx, which basically means that we cannot, when we go to integrate it, we raise it by a power, it becomes x to the 0 over 0, which cannot be done. So that's where we are, that's where we're struggling with this. So the rule is basically that we get the natural log of x for this, and it's because 1 over x and the natural log of x kind of are the way the graphs of the functions are. We're restricting the domain of 1 over x, and we'll end up getting this natural log function. So make sure that you remember these. There are properties of the natural log function, and if you need to pause any of this, please pause it and get it down. There are properties of natural log functions that we need to remember, that the domain is between 0 and infinity, and the range is from negative infinity to positive infinity. It's continuous, increasing, and 1 to 1, and the graph is always concave downward. And then these 4 properties down here, these should be a reminder from pre-calculus and from maybe algebra 2, but you need to make sure that you have these for this section and sections beyond that. So pause it if you need to, because we're going to use those properties as we go along here. So in the first example, I am asked to expand these, and this is just using those properties that we had before. So if I want to expand this, this is just kind of a little algebra 2 review. This could be written as the natural log of 10 minus the natural log of 9, and that would be my final answer for that one. This guy, if I'm saying the square root of this whole thing, then remember that a square root, a function, is really the same thing as, this could be written as the natural log of 3x plus 2 to the 1/2 power. And so if I'm going to do that, the first thing I'm going to do is I'm going to move the 1/2 out front, and then I have the natural log of 3x plus 2. And so that would be my expanded form of this, and it actually helps me get rid of exponents, and you'll see as we start doing differentiation and integration of these things that life becomes much easier if we can get rid of some of these exponents. In the next one we have the natural log of 6x over 5, and to expand this one out I would write it as the natural log of 6x minus the natural log of 5. But then I could, if I wanted, I could expand 6x out even further because it's a multiplication. So I might get the natural log of 6, which is some number, plus the natural log of x, which we know what that is in integration form, minus the natural log of 5, which is another number. And so that could help us along the way. And then we get to this really convoluted one down here that says the natural log, and this is more like what we're going to see when we do this stuff. Maybe something looks like that, over x, and it is the cube root, x times the cube root of x squared plus 1. So when I go ahead and expand this out, well, the first thing I'm going to do is break apart this division problem. So write it as 2 natural logs. So it's going to be the natural log of x squared plus 3 squared minus the natural log of x times the cube root of x squared plus 1. So that would be how I'd start this, and then I'd start trying to get rid of exponents and any other addition and subtraction that I can deal with, or any other multiplication I can deal with. And so to continue this on, this becomes, like I said, kind of, I can put the 2 out front. So I get 2, the natural log of x squared plus 3. Remember, there are no rules for breaking up natural logs with addition and subtraction, so this is as far as this part will go. Over here I have these parts are being multiplied together, the x times the cube root. But the thing is, since I'm already subtracting, this whole thing is kind of in parentheses. So I'm going to subtract the natural log of x and subtract the natural log of the cube root of x squared plus 1. And then really the only thing left for me to do is put the 1/3 out front to get to my final answer. And so it's 2 natural log of x squared plus 3 minus the natural log of x minus 1/3 the natural log of x squared plus 1. So that's really what we're looking at for this problem, and we need to practice expanding these things because we will need them as we go along. Well, the next one here is just kind of, so basically you make sure you get this definition of e. In the natural log of e, hopefully you know is 1, and basically it's the same as saying taking the integral from 1 to e of 1 over t dt. So we end up with the same thing. So we're going to be dealing with these as we go along, and so basically what I want you guys to do here, this is just testing to see if we can, our calculator skills are okay. So the natural log of 2 is approximately 0.693. Just punched it in my calculator, hit enter, and got it. So the natural log of 32 is 3.466, and the natural log of 0.1 is negative 2.303. So check with your calculator and make sure that you're getting the same answers, because otherwise we need to talk about this. So then in the next section here, where this is our definitions of the derivative, if we take the derivative of the natural log of x, we get 1 over x. And if we take the derivative of the natural log of some other function, then we basically get 1 over the function times the derivative of that function. And how I remember this is, for both of these, it's, in my book, it's u prime over u. So if I'm going to do the derivative of the natural log of x, the derivative of x is u, then it's 1, the derivative of x becomes 1 over the original x. So if I'm going to do this, we're going to practice a couple of these. I've got 4 examples here. And so just remember, if I'm asked to take the derivative, I'm looking for u prime over u. And so my u value in this case is 2x. 2x equals u, and so then u prime is going to be 2. So my final answer for this one is going to end up being, giving me 2 over 2x, 2 over 2x, u prime over u, which is really equal to 1 over x. It just happened that we got back to where we started. So the next one, well, if I'm going to take the natural log of this, I'm going to say u is x squared plus 1. Then u prime will be 2x. And so now if I do u prime, I get 2x over x squared plus 1. Can I simplify this anymore? No, I cannot, because remember that there's a plus sign, so it doesn't simplify much inside there. So then the next one, so hopefully those weren't too bad for you. This time it's still u prime over u. The issue is if u is equal to x, then u prime is 1. But how are we going to deal with this x times the natural log of x? Well, that times, that multiplication, should make you think product rule. So again, that's what we have to do. We have to do the product rule. So I'm going to differentiate the first, which will give me, so if I go through and differentiate this and say this was equal to y, I'm going to call it y prime. If I differentiate x, I just get 1 times the natural log of x. Then I'm going to add on, well, if I leave x alone and differentiate ln of x, I get 1 over x. So there's my product rule. My final answer when I differentiate this is ln of x plus 1. And I might even go as far as putting 1 plus the natural log of x, just so that I don't get confused that this, if I don't use parentheses and I get kind of lazy, sometimes I forget to use parentheses around there, and I might end up with thinking that this 1 is with the x, which it really isn't. It's the vertical shift of the graph of the function. So then we get something that looks like this, and you're probably saying, well, I could do this as a big long product rule, or the other thing is that this is the chain rule. And so things to remember from way back when, that we need to remember these things. And so this is still u prime over u, but in order to do the derivative, we've got to do the chain rule. So if I'm going to do the derivative of this function, so if I said u was x, then u prime is not going to help us much, but we can go ahead and do the derivative of this. So the chain rule says do the derivative of the outside, which would be 3 ln of x all squared, and then we're going to multiply by the derivative of the inside, which happens to be 1 over x. And so if that's the case, then the best I can do for my answer is 3 ln of x all squared, maybe times 1 over x, or I might even do like 3 over x ln of x squared. I don't know, it just depends on how they want it simplified. So that's kind of what we're looking at for this one. And so then my final example that I'm going to do is basically we're going to use our properties to help us get through this differentiation. So basically our breaking it up properties are logarithmic properties. So in this case we have f of x equals natural log of the square root of x plus 1. Well, remember that I could write this before I do any differentiation. I can write the square root as x plus 1 to the 1/2 power. So then that means that I could really write this, instead of having to do a chain rule on the inside, I could put the 1/2 out front, which is a constant multiple, which makes my life a heck of a lot easier to get this. And so I can write it as 1/2 ln of x plus 1. Now this is my u value, so my u value is x plus 1. My u prime is 1 when I do my differentiation. So now the only thing I have to worry about is when I go ahead and do my differentiation is to leave the 1/2 out front. And then u prime is 1 over u, which is x plus 1. And so that would be my final differentiation of this. And maybe I would write it like this, 1 over 2 times x plus 1, or some form of that. But that's really all we're talking about with these. So we will cover more of this stuff in class, so please come prepared to class to ask your questions. Thank you.